Okay, this is chapter 2, section 1, conditional statements. We're now getting into proofs. Essential question: when is a conditional statement true or false? A conditional statement symbolized by P then Q, if P then Q is how you read that, if P then Q, can be written as an if-then statement in which P is the hypothesis and Q is the conclusion. Here's an example. If a polygon is a triangle, then the sum of its angle measures is 180 degrees. The hypothesis is P. It's everything after the word if and before the word then. You don't include the word if in the hypothesis. The conclusion follows the then statement or the then word, but not including it. So then the sum of its angle measures 180 degrees. The conclusion is the sum of its angle measures is 180 degrees. So what you will learn in this chapter is to write conditional statements, use definitions written as conditional statements, and write biconditional statements, and make truth tables. Okay, so let's dive right in. Okay, the core concept for writing conditional statements is a conditional statement is a logical statement. Okay, logic is the foundation of mathematics. It's a logical statement that has two parts, a hypothesis P and a conclusion Q. When a conditional statement is written in the if-then form, the if part contains the hypothesis and the then part contains the conclusion. So in words, you'd say if P then Q, and in symbols, it's P arrow Q, and it's read as P implies Q. You could either say if P then Q, or you could say P implies Q. Okay, example 1 says rewriting a statement in if-then form. Use red to identify the hypothesis and blue to identify the conclusion. Then rewrite the conditional statement in if-then form. So here the key word is all. All birds have feathers. So the hypothesis would be all birds or just birds. All birds. Keyword is all. And the conclusion is they have feathers. Okay, so all birds have feathers. All birds, red, hypothesis, have feathers, conclusion. I want to write that in an if-then statement, so I'm going to just type instead. So let me do this, and how about in red? Okay, so how do I say all birds? What are, so we have to start off with if, and what are birds? They are animals. So you say if an animal is a bird, comma, space, switch to blue, then it has feathers. Okay, so if an animal is a bird, then it has feathers. So the only thing I want to do, it is an if-then form, but keep in mind that the word if is not part of the hypothesis and then is not part of the conclusion. So what I really should do here in showing this, if we're going to do it color-coded, is make this black. Oops. Okay, so this is how it should be written. So an animal is a bird is the hypothesis. It has feathers is the conclusion. Okay, so there's A. So we're going to do this again for B. Now it says you are in Texas if you are in Houston. So notice where the if is right here. So what follows if is your hypothesis. And what you end up with is your conclusion. So you don't want to say if you are in Texas, then you are in Houston, because I could be in Dallas. I could be in Austin. So you don't want to say it that way. So you want to say the hypothesis first, the if portion first. So in doing this, I will switch back to this. And I would say if, then switch to red for my hypothesis. If struggling here. If you are in Houston, comma space, switch to black, then switch to blue. I thought I switched that to blue. You are in Texas. So if you are in Houston, then you are in Texas would be an if-then statement of you are in Texas if you are in Houston. And the you are in Houston is the hypothesis, and the you are in Texas is the conclusion. Okay, another core concept is negation. The negation of a statement is the opposite of the original statement. To write the negation of a statement that we're going to call P, remember P is the hypothesis, you write the symbol for negation, which is a tilde. Tilde. Anyway, it's the squiggly line before the letter. So not P is written tilde P. The words are not P. The symbol is that squiggly line P. Okay. Okay, example 2 says writing a negation. It says write the negation of each statement. The ball is red. So if a ball is red, that's the original. Opposite of is red is not red. It's pretty simple. So all we're going to do is say the ball is not red. Okay, so there's the negation of the ball is red. The ball is not red. Don't give a counterexample. If it says the ball is red, don't say the ball is blue. You have to say the ball is not what they originally said. Okay, now B, the cat is not black. All right, so now we want to negate that. Well, if the cat is not black, if we want to do the opposite, then the cat has to be black. So you'd say the cat is, and you don't say not, we don't use double negatives. The cat is. Actually, let me just do this. And let me change this to red because I can't put not in there. So the cat is black. You just get rid of the not. Okay, so here's another core concept, related conditionals. Consider the conditional statement below. Words, if P, then Q, symbol P, arrow Q. The converse, to write the converse of a conditional statement, exchange the hypothesis and the conclusion. And the way I try to get students to remember this is think of Converse sneakers. Put them on the wrong feet. Take the left shoe off, put it on the right foot. Take your right shoe off, put it on your left foot. That's converse, switching the P and the Q. So in words, it'd be if Q, then P, and the symbol would be Q arrow P, meaning Q implies P. So the inverse, to write the inverse of a conditional statement, negate both the hypothesis and the conclusion. So if we had the words, if not P, then not Q, would be the inverse of if P, then Q. You'd negate both. Symbol is not P implies not Q. Contrapositive, write the contrapositive. That is a combination of converse and inverse. That means you switch the, where are my hands? That means you switch the hypothesis and the conclusion and negate both. All right, so to write the contrapositive of the conditional statement, first write the converse, then negate both hypothesis and the conclusion. So if we originally had if P, then Q, it's going to end up being if not Q, then not P. So the symbol is not Q implies not P. Okay. A conditional statement and its contrapositive are either both true or both false. Similarly, the converse and inverse of a conditional statement are either both true or both false. We'll get into that when we do our tables. In general, when two statements are both true or both false, they are called equivalent statements. Okay, let P be you are a guitar player. Let Q be you are a musician. Write each statement in words, then decide whether it is true or false. A, the conditional statement P, then Q. Okay, so I guess I'll just type this. It's easier because my handwriting is not the best. All right, so they want a conditional statement P, then Q. So you would say, if you are a guitar player, then you are a musician. Okay, let me just move that. The converse of that would be Q, then P. If you are a musician, then you are a guitar player. Okay, so notice the difference here. The if statement became the then, and the then statement became the if. They switched. Now the inverse, you negate P and Q. So that would be not P, not a guitar player. If you are not, let me do that in italics. If you are not a guitar player, whoops, then you are not a musician. Okay, if you are not a guitar player, then you are not a musician. We'll get to their truth values here in a moment. And then finally, they want us to do the contrapositive, which means take the hypothesis and the conclusion, switch them, and negate both. So I'm going to start with you are a musician and negate it. So I'm going to say, if you are not a musician, then you are not a guitar player. And again, let me italicize these nots. Let me line these up. Okay, so here they are. So if you are a guitar player, then you are a musician. If that is true, if you are a guitar player, then you are a musician. That is true. But if you take the converse, if you are a musician, then you are a guitar player, that is not true. You might be a piano player. If you are not a guitar player, then you are not a musician. That's not true. If you are not a guitar player, but you play the piano, you are still a musician. And then if you are not a musician, then you are not a guitar player. That is true. If you're not a musician, you're not a guitar player, piano player, or any instrument player. So the original is true, then the contrapositive will be true. Okay, so now we're going to use definitions. And it says you can write a definition as a conditional statement in if-then form or as its converse. Both the conditional statement and its converse are true for definitions. For example, consider the definition of perpendicular lines. If two lines intersect to form a right angle, then they are perpendicular lines. The converse to that would be, if two lines are perpendicular lines, then they intersect to form a right angle. You can write line L is perpendicular to line M as L, looks like an upside down capital T, but that's a perpendicular symbol. M. So L perpendicular to M. Okay, now let's get rid of that and do example 4. Using definitions. Describe whether each statement about the diagram is true. Explain your answer using the definitions you have learned. So it says A, line AC, the horizontal line here, is perpendicular to line BD. Okay, so what I want to point out to you here is this right here. This tells us it's a right angle, and when we have a right angle, then we have two lines perpendicular. So this symbol right here in the diagram tells us that this is true. So A is true. Okay, decide whether each statement about the diagram is true. So I'm going to put a T there. That was true. Now B says angle AEB. So let's mark it. Actually, it is marked. It's angle AEB, where this red right angle symbol is. Angle AEB and angle CEB are linear pair. Okay, well, the definition of linear pair means that if you have two angles on a line, both on the same side of the line, so angle AEB and angle BEC are above line AC. Let me highlight that before I continue. There's a lot of things going on here. Let's make that a line a little bit thicker, and I'll use red. So we're talking about this line AC. All right. Angle AEB and angle CEB are both above the red line AC. And if AEB is 90 degrees, then angle BEC has to be 90 degrees because AC is a straight line and that's 180 degrees. So from here to here is 180 degrees. So if half of it's 90, then the other half has to be 90 degrees, and therefore that would form a linear pair. And by definition, a linear pair are two lines or two angles that share a common side, which makes them adjacent. Two adjacent angles, sum is 180 degrees. So this is true. And then finally, rays. Now we're talking about rays, so let's get rid of this line. Okay, so now I'm going to do a ray. Ray EA is right here. And ray EB, I'll do in green, is right there. It says ray EA and ray EB, excuse me, are opposite rays. Well, that's not true. Ray EA and ray EC are opposite rays. So this is false. Okay, now we're going to write what is called a biconditional statement. A biconditional statement, when a conditional statement and its converse are both true, you can write them as a single biconditional statement. And a biconditional statement is a statement that contains the phrase if and only if. And the symbol is double arrows, as you can see right here. Any definition can be written as a biconditional statement. So if I go back to that last problem and talk about linear pairs. Okay, if two angles are linear pairs, then their sum is 180 degrees. If two angle sums are 180 degrees, then they are linear pairs. I'd have to think about that one right there. If a triangle is a right triangle, then one of its angle measures is 90 degrees. That is true. If a triangle has an angle of 90 degrees, then it is a right triangle. So there's an example of it being true both directions. Record. Okay, example 5, writing a biconditional statement. It says rewrite the definition of perpendicular lines as a single biconditional statement. Remember, we can write them biconditional if the original is true and the converse is true. So it says definition. If two lines intersect to form a right angle, then they are perpendicular lines. So here is line S, here is line T. They intersect, form a right angle, therefore S is perpendicular to T is true. So I'm going to, before I answer this as a biconditional statement, I'm going to write it as the converse. So you'd say if, and you start with the conclusion, but you don't say they. You always have to give, and you have to explain what they are in the if portion. So I won't say if they are perpendicular lines. You'd say if two lines are perpendicular, then they intersect to form a right angle. Okay, so that is the converse, Q then P. And think about that. If two lines are perpendicular, they intersect to form right angle. That is true. Okay, so the definition is true. The converse of the definition is true. And now I can state it as a biconditional statement. So I'm going to start with black. And you'd say two lines intersect to form a right angle if, and let me put that in a different color. This is the key to this. If and only if they are perpendicular lines. Okay, so instead of writing the definition and then the definition's converse, you can simply write the two as an if and only if statement, biconditional. So now it says two lines intersect to form a right angle if and only if they are perpendicular lines. So how would I write that? Well, let's take a look at now using symbols. So if two lines, so the hypothesis is after the word if. That's my P. The conclusion is after the word then. That's my Q. Now I'm going to say P if and only if Q. And that's how that would be written using symbols. Okay, making truth tables. The truth value of a statement is either true T or false F. You can determine the conditions under which a conditional statement is true by using a truth table. The truth table below shows the truth values for hypothesis P and conclusion Q. So when you have two things that can either be true or false, then the possible number of outcomes is 4. And they both can be true, they both can be false. The first can be true, the second can be false, or the vice versa, the converse, the false hypothesis, true conclusion. I'm going to bring this box down and put it right here for a reason. In a truth table, the only time in a conditional statement, so this is the hypothesis, this is the conclusion, this is the conditional P implies Q. The only time a conditional statement is false is when the hypothesis is true and the conclusion is false. So the conditional statement P implies Q is only false when a true hypothesis produces a false conclusion. Two statements are logically equivalent when they have the same truth table. Okay, so here's example 6, making a truth table. Use the truth table above, well, it's to the right in this case, to make a truth table for the converse, inverse, and contrapositives of a conditional statement P implies Q. So here's the table from before: true, 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 false, false, true, false, false. And that's what you always start with in every table. PQ, true, 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 false, false, true, false, false, and so on and so on. P and Q don't ever change, so we're going to use those truth values in each table. And then we're going to, the P implies Q is true, false, true, true. The only time it's false is when you have a true, if true, then false statement. Okay, so here's the converse, Q, then P. So now we're going to have, that would be T, then T. If true, then true, well, that would be true. And then it says, if false, then true, that is true. And the only time a conditional statement is when the hypothesis is true and the conclusion is false. And here's a true Q, then a false P. So that's going to be false. And then false, false is true. Okay, so there's the converse. Q implies P. Now we're going to do the inverse. Okay, well, if you first say the ball is red, and now you're saying the ball is not red. If the ball is red was true, and you say the ball is not red, well, that would be false. So the inverse is always the opposite truth value of the original. So if P is true, not P will be false. If P is true, not P will be false. If P was false, not P would be true. And if P was false, not P would be true. And then the same goes for Q. If Q is true, not Q is false. If Q is false, not Q is true. If Q is true, not Q is false. And if Q is false, not Q is true. Now the conditional statement, remember, we're doing not P, then not Q. The only time it is false is when you have a true, then a false. So this is false. True, true is true. False, true is true. And false, false is true. So true, true, true. Okay. All right. Now the contrapositive, not Q. Okay. That's the opposite of true. That's false. Not Q. The opposite of false, true. Not Q. Opposite of true, false. Not Q. The opposite of false, true. Not P. The opposite of true, false. Not P. The opposite of true, true, false. Opposite of P. I'm sorry, not P. The opposite of false, true. Not P. The opposite of false, true. Now when we do not Q implies not P, we're starting here and going to here. Q, not Q, then not P. False, false, true. True, false is the only time it's false. False, true is true. And true, true is true. And there are the three tables filled in, converse, inverse, contrapositive, for the initial conditional statement. So I just wanted to say something about this. In order for us to get to a truth table with P implies Q, and it's contrapositive, not Q implies not P, we had to do a table for the converse. We had to do a table for the inverse. And then we had to do a table for the contrapositive. Okay, that brings us to the end of chapter 2.1, to the exercises. These are the problems I'd like my class to do. Have a great day.